This is Unit 13, Thermochemistry, Part 1 Notes. By the end of this unit, you should be able to understand energy and its forms through energy transformations of chemical and physical reactions. You should also understand the law of conservation of energy, understand the process of heat transfer, meaning the direction of heat flow in terms of the system versus the surroundings. And you should be able to perform calculations involving heat, mass, temperature change, and specific heat. Thermochemistry is the study of energy changes that occur during chemical reactions and changes in state. And this changes in state refers to any type of physical change going from a solid to liquid to gas. So going back to your phase change diagram. And if you look over here, melting and heating or freezing, any of those things, that is considered a physical change. And we can analyze the energy flow in terms of chemical reactions or physical changes. Energy is the ability to generate heat or do work. If you do work, that relates to physics topics. So we're really going to focus on just the generation of heat and understand the flow of that energy to and from different substances. There are different types of energy, or there's different forms, and we need to be able to understand at least 4 different types, if not all of these. Chemical energy is the energy stored in chemical bonds of substances. This is also known as chemical potential energy. So there is chemical energy that is stored within the bonds of any substance. That is why we eat food. We eat food so we can break it down through this cellular respiration process, and that creates ATP. So whenever you think about bonds within compounds or elements, they contain a specific amount of energy, and whenever we break apart those bonds and reform bonds, that can also lead to energy, and that's going to be in our Part 2 lecture focusing on the bonds. Our potential energy is stored energy either based on physical position, so like a height, or chemical composition. So chemical energy can potentially almost be considered potential, but they kind of relate to one another because there is energy stored within those bonds. If you think about potential energy, if you're on top of a waterfall and you fall down, you have a lot of potential at this height. Once you hit the ground, you're at level 0. Now you have no more potential energy stored. We're really going to focus on just the chemical composition in this class. Kinetic energy is the energy of movement. So how do we measure temperature of the air? We just analyze the movement of the gas particles, and that either allows the mercury to travel up or down the thermometer, and that's based on the movement of particles. So anytime you think of movement, that is going to be your kinetic energy. And then we have thermal energy. Whenever you think of thermal, that is your heat. So that's transferring from one object to another because of a temperature difference. Okay. Heat travels from hot to cold. You must know this. Okay, so anytime you have energy, it's going to travel from hot to something cold because you want to create this equilibrium between anything that has a temperature difference. So again, you travel from hot to something cold. There are other types of energy, like electromagnetic energy. We learned about the electromagnetic spectrum a couple 6 weeks ago. But that also has a form of energy because we analyze the energy based on frequency and wavelength. Thermal, this is going to be your heat, inputting heat or taking heat out. You also have a mechanical energy, and that's being able to move different types of objects, either based on your own mechanics or based on the mechanics of, let's say, an automobile. You do have nuclear energy. We talked about fission and fusion. That does release some sort of energy. Chemical energy, that's within the bonds. And then obviously we have electrical energy because that's how we have light in through the power lines, or even lightning has a potential amount of energy. The law of conservation of energy is where energy cannot be created nor destroyed. And we learned this type of law whenever we were balancing chemical reactions because we have to abide by that law of conservation of mass. So mass cannot be created nor destroyed. Same concept. Energy cannot be created nor destroyed. It can only be converted between the different forms that we discussed on that previous page. The amount of energy in the universe is fixed. There can be no more energy produced, and we cannot take away any energy. It is a fixed amount. And so we can abide by this general rule where the energy of the system, which is part of the universe where we are actually analyzing, that's where the physical or chemical reaction is occurring. So the energy of the system plus the energy of the surroundings will equal the energy of the universe. So like I said before, the energy of the system, that is where the reaction is happening. Everything that's not the system is called the surroundings. So whenever you're talking about energy transfer, you can specify what that system is. So once you analyze that system, everything that's not the system is going to be that surroundings. And it will always equal the energy of the universe. So if the system decreases, that means the energy of their surrounding is increasing, and vice versa. You can never, well, if you lose energy, it's lost in the form of heat, but the energy in this world is fixed, so we have to abide by this general rule. So again, the system is part of the universe where the reaction is occurring. You set that, and everything that's not this system is going to be called the surroundings. So whenever you analyze the direction of heat flow, the system is always used as the point of view. Is the heat going into the system, or is it coming out of the system? If heat is transferred from the surroundings into the system, that is going to be your endothermic process. Okay, so think about trying to heat yourself up on the couch. You know, you have your nice little video, cell phone out, and you sit by a fire. Well, the energy is traveling from the fire into your body because you want to get warm. Think about endothermic is entering the system, so heat is going into the system. And then if heat is being transferred from the system to their surroundings, so you're going out of the system, anytime you're exiting the system or going out of the system, that is going to be exothermic. So when you get really hot playing a sport and you give off a lot of energy or a lot of heat, that is an exothermic process. So endothermic, heat is being transferred into the system, and it's going to have a positive concept. Exothermic is going to be a negative concept. So keep that in mind whenever we start doing calculations. Endothermic will always be positive because it's entering. Exothermic, whenever the heat or energy is leaving, it's going to be considered a negative process. So we can measure the amount of heat transfer either in the unit joules or calories. Okay, these are going to be two new units that we're going to be talking about. So 1 calorie is going to be equal to 4.18 joules. This is an equivalent, so if you ever have to convert between one or the other, please make sure you're using dimensional analysis. So specific heat is defined as the quantity of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. So we can analyze how easily heat can flow in or out of a system based on this specific heat value. So specific heat is to analyze how easy or how efficient it is to lose or gain energy. And the higher the specific heat, the more difficult or the more energy that you have to input into the system to raise that specific amount by 1 degree Celsius. The lower the specific heat, the easier or the less amount of energy you can input to heat that up. So why do you think water takes forever to heat up and boil? Well, water has a very high specific heat. It's actually 4.18 joules per gram degrees Celsius. So anything over the value of 1 is going to take a lot of energy to heat up. And every substance has a unique specific heat, just like every single substance has a specific density. Okay, that value is intensive. It's never going to change. Doesn't matter if you have 1 gram, 2 gram, 5 million grams, it's going to have the same specific heat. And our formula is here. Q is equal to mc delta T. This is my MCAT formula. So whenever I say MCAT, we're talking about specific heat. Your Q value is going to be your heat. If it's an endothermic process, your Q is going to be positive. And if it's an exothermic, your Q is going to be negative, just as I spoke previously on the last slide. Mass is the letter M. Specific heat is C with a sub P. And then your delta T, that's going to be the change. So anytime you have a triangle, that is going to mean change in. The units for the specific heat formula are as follows. Heat will be in joules or calories. Mass will be in grams. Temperature can either be in degrees Celsius or something known as Kelvin. Please be aware of your specific heat formula. If it's given in joules per gram, grams times degrees Celsius, then you can just use degrees Celsius. But if it's in joules per gram Kelvin, you need to be aware because you might have to convert between degrees Celsius and Kelvin. It's very simple because 0 degrees Celsius is equal to 273 Kelvin. That is an equivalence. So if you're given degrees Celsius and you have to convert to Kelvin, you're just going to add 273 to degrees Celsius to get your Kelvin. For example, if you have to calculate Kelvin of 20 degrees Celsius, you just add 273, and then you get 293 Kelvin. All you're doing is adding 273. And if you're going from Kelvin back to degrees Celsius, you will just subtract 273. So you need to be aware of the units for each of the following variables, because if you assume that anytime you see this joules, that's heat, the joule per gram degree Celsius, that is specifically the specific heat. So a lot of students get heat and specific heat mixed up, and that will make your calculations incorrect. Okay, so then to perform specific heat calculations, you first have to be aware of the question being given. And anytime you see the word specific heat, automatically think, all right, this is a specific heat calculation. You can't see your formula down there. I try to put it on there. It's going to be Q is equal to MC delta T, and this should be on your formula chart in the thermochemistry section. So the question is asking how much heat. Okay, so how much heat, that is going to be your Q variable. How much heat is required to raise the temperature of 250 grams, that's your mass, of mercury 52 degrees Celsius. So you're raising it a total of 52, so that's going to be your change in. And they give you the specific heat is 0.14 joules per gram degree Celsius, and that is your C value. So if you're looking for heat, you're looking for Q, and Q is the multiplication process of M times C times delta T. Whenever you have variables next to each other, you are multiplying. So your mass is 250, your C is 0.14, and then your delta T is 52. So multiplying all three of those values together, we get 101,820 joules, and it is a positive Q, so this would be an endothermic process because you have to input it into the system. And then converting this to sig figs, you need 2 sig figs, so I'm just going to use scientific notation, where I get 1.8 times 10 to the third power, because we move it 1, 2, 3 times, and joules. The next problem is saying when 435 joules of heat is added, so if you add heat to something, it's going to be a positive 435 joules because it's going into the system. Heat is your Q. You add it to 3.4 grams, that's your mass, and you are going to input it at olive oil at 21 degrees Celsius. If the temperature increases to 85 degrees Celsius, and then you're asking what is the specific heat of the olive oil. Okay, so what is the specific heat? That is your C. So you originally start with Q is equal to MC delta T. Okay, and if you're solving for C, you have to get C by itself, so we're going to divide both sides by M delta T because we have to get rid of everything next to it. So C is going to be Q, which is your heat, divided by M times delta T, and you must perform M times delta T first before you divide. Your Q is a positive 435 over the mass, which is 3.4, and you're going to multiply that by delta T. Well, delta T is final temperature minus initial. Okay, if you want to raise it to 85 degrees Celsius and you originally started at 21, your delta T value is going to be that difference, which is 64 degrees Celsius. Okay, so then you take 435. The product of 3.4 times 64 is 217.6. And then 435 divided by 217.6, C is going to be equal to, let me erase that real quick. C is going to be equal to 1.99999, that's repeating. Your sig figs, all those numbers have 2 sig figs, 435 is 3, but use the least amount. So C is going to be equal to 2.0 joules per gram degrees Celsius. Alright, so have you learned the objectives of this unit? If not, please return back to the original slide and rewatch any of the videos, or if you have any questions, please make a mark in your notes to where I can go over them in the next lecture in class.